I see it. Okay.
Buenos días nuevamente. Vamos a continuar con el programa del quinto simposio de la red de investigación interdisciplinaria en Quiralidad. La segunda conferencia está a cargo del doctor Jean-Claude Michaud, que también nos acompaña desde Francia. Salut, doctor Michaud, et bienvenue. El doctor Michaud se graduó de la Escuela de Química de Toulouse, realizó estudios de doctorado en el área de fotoquímica orgánica y posteriormente se desplazó a Bruselas para realizar una estancia postdoctoral bajo la dirección de Ilya Prigogine. Sus intereses en investigación se centran en el estudio del fotodicroísmo, la dinámica química no lineal, mecanismos de reacción y, por supuesto, quiralidad. El doctor Michaud es autor de más de 170 artículos y capítulos de libro. Ha sido galardonado con la medalla de bronce del Centro Nacional de la Investigación Científica de Francia, o CNRS, en 2014, y le fue otorgado el doctorado honoris causa por la Universidad Rostov-on-Don de Rusia. Actualmente se le ha distinguido como investigador emérito en la Universidad de Toulouse Paul Sabatier. El título de su conferencia es A Journey to Chirality. Dear Jean-Claude, thank you very much for accepting our invitation. We are very happy to have you here. The floor is yours. I will notify you 5 minutes before the end of the 40 minutes you have to develop your topic. Is it okay?
Yes, it's okay. Thank you very much. Thank you for your kind invitation, Sandra, and thank you for the organizing committee to invite me to give this talk today from France to Mexico. It's the first time that I am using this kind of Zoom conference, so I will try to use in the best way.
Okay, please, you can start when you are ready.
It's yeah, I will try again. So the title is A Journey to Chirality. So I will try to find this title to have a general view on chirality, and for me, I will try to give some pedagogical concept for the students, since the talk is retransmitted by YouTube. So I will try to define firstly the chirality. Yes, so you see something here or not?
Yes. We see your up screen.
No,
I don't see it.
Again.
Okay, now we see it.
Yes, you
Excellent.
see here the word chirality is derived from the Greek kir, which means hand. And you see a picture of the la Cueva de las Manos, and you see many hand stencil. You see the hand stencil, and I can ask you how to recognize left from right. In fact, it is a problem. The right versus left recognition problem is not so easy. Look what say Winnie the Pooh. Pooh looked at his two paws. He knew that one of them was right, and he knew that when you have decided which one of them was the right, then the other one was the left. but he never could remember how to begin. And why? Because this problem is more complicated, because only chiral system can recognize chirality. And look at this dashboard. One is real and the other is mirror image. And I give you a few seconds to let you to choose. It's a difficult task, but now I can give the chiral reference. And the chiral reference is this. And from this, you can see that here is real. And this is a mirror image. You see the difference here and here. So this is an example. What is the chiral reference? And to illustrate the chiral reference question, I would like to give you some example of chiral reference in the laboratory everyday life. So Cornelia has already spoken about chiral HPLC. So what is the principle of the chiral HPLC? This is the first, my first example. The principle is based on the 3-point attachment. Here, this is a chiral stationary phase, and this is a 2D chiral system. It is flat, it is a surface, and it is an asymmetric carbon. When the asymmetric carbon match easily with the chiral stationary phase, is attached. So when it is matched, it remains attached. But when the enantiomer is mismatched, and so the attachment is difficult. And during the elution, what is mismatched is eluted before than the other. So the two enantiomers can be separated. This is the principle of the chiral HPLC. But we have already seen that in the first talk by Cornelia, that it is not so easy to obtain this chiral stationary phase. The principle of the recognition, the chiral recognition, is based on the so-called diastereoisomeric interaction. So this is the chiral reference, and this is the two enantiomers, and they form a diastereoisomer, RR on one side, SR on the other side, and these two diastereoisomers are different. And this is the principle of the chiral recognition. So for the use for the making of this chiral stationary phase, the silica surface is linked with some natural product here, for instance, the beta cyclodextrin to recognize the sugar. This is a cavity which is formed by 7 glucose molecules. All is a natural product, and the chirality is enantiomerically pure. So this is the first example of the chiral recognition. A second example is given by the NMR shift reagent. We can say that nuclear magnetic resonance, the NMR, is unable to discriminate the two enantiomers of chiral molecule because in the absence of any chiral reference, the spectral parameters are identical. For instance, if you take this phenylalanine compound, ethylphenylamine amine compound here, the R and S enantiomer give exactly the same spectrum. To differentiate the two enantiomers, we need to use a chiral reference to play with the same diastereoisomeric interaction, the recognition between, not between the enantiomer pure, but between their image in diastereoisomeric image. For that, they use a chiral reference, and in this case, this is an europium complex, which is made from a natural product, which is a camphor natural product. And here you see that the RR and SS give two different signals. That is the principle of the NMR shift reagent. And so this is a message to remember that in the absence of any chiral reference, enantiomer, in absence of any chiral reference, enantiomers are identical. I put quotes here because we will see that, in fact, this is not exactly true. From the practical point of view, they are identical, but theoretically, we will see that they are not really identical. To illustrate the message of the identity of the two enantiomers, I give you here two situations showing the enantiomer identity. The first one is called prochirality. Consider this aldehyde. The aldehyde is planar, is flat, and the two sides of the plane are identical. And when there is a nucleophilic attack on the aldehyde, the two faces, either what's called the C face or the Re face, they appear identical to the nucleophilic agent because the nucleophilic agent is non-chiral and it cannot recognize that the methyl is on the left or the methyl is on the right. And so it gives an enantiomer in 50-50. This is what we call the racemic mixture. So when we add no chiral reference, the product is enantiomerically impure, is racemic. We have 50-50. Another situation, which is rather similar from the point of view, from the geometrical, from the topological point of view, is the racemization. Consider an asymmetric carbon, tetrahedric carbon, and remove one substituent, and you have a flat trigonal carbon. And to return to the initial product, we add again the substituent A, but also we cannot recognize right from left, and so you obtain the enantiomer. So you obtain two enantiomers, and the probability to return on right or on left is the same. There is a 50-50 probability, and the mixture becomes racemic. So this is what's called a racemization. But the question is how to make the two faces different. The response is to use a chiral reference. And this is the principle of the asymmetric synthesis. So this is the principle of asymmetric synthesis. It is based on the diastereoselective interaction, the use of a chiral auxiliary. Sometimes the asymmetric synthesis is called stoichiometric. This is the amount of chiral auxiliary is stoichiometric to the product, to the substrate. Or the most interesting is the enantioselective reaction. the enantioselective reaction, there is only a chiral catalyst. And the result of the asymmetric synthesis is that the two enantiomers are produced not in the same amount. There is a major product and a minor product. And to make a measurement of the difference between the amount of the two amounts, we define the enantiomeric excess, which is the difference of the amount of R and S enantiomer divided by the sum. This is the enantiomeric excess. And also now a question arises. What is the origin of the chiral catalyst? The origin of the chiral catalyst is the so-called chiral pool. The chiral pool is a collection of abundant enantiopore building blocks provided by nature and used in asymmetric synthesis. So for those who like beautiful molecule, I give you the formula of ephedrine, strychnine, sparteine, tartaric acid, the well-known tartaric acid by Pasteur, the proline with one asymmetric carbon, and one very beautiful called diisopinocamphényl boron, a catalyst which is used in asymmetric synthesis. But there is a fundamental question. What is the fundamental question? Since all the chiral compounds are either natural or derived from a natural product, what is the origin of the natural chirality? A question which was already discussed by Cornelia. In fact, there is no clear-cut answer. Difficult to respond to this question. What is the origin of chirality? However, we are already soon this Murchison meteorite. Large amount of enantiomeric excess in some meteorite provide evidence that the transition to homochirality would have been initiated by some abiotic mechanism before the start of life. But in this case, what are the chiral references? The first one, there are many. In fact, there are many possible chiral references, but I will speak only about two. One is we have already seen in the previous conference. This is a highly circular polarized light coming from the Orion massive star-forming region. Everybody knows the Orion constellation, and what is interesting is the Orion Nebula. In the Orion Nebula, there is, it has been found some regions which are emitting a circularly polarized light. The circularly polarized light, in this case, infrared, because there is a dust, too much dust to pass the UV, but in fact, it is probably UV light is already circularly polarized light, and circularly polarized light is a true chiral force, because the electromagnetic field is rotating, is describing a real spiral. And as we have seen also in the previous talk, this circularly polarized light is able to perform asymmetric photolysis. And I will explain again what is the principle of the asymmetric photolysis. We consider two enantiomers, R and S, for instance, and due to the circular dichroism property, the Cotton effect, each enantiomer absorbs the circularly polarized light in a differential way. This is a so-called G factor. And so if I irradiate with a circularly polarized light a racemic mixture, you see that the size of the two enantiomers are exactly the same. Both enantiomers are destroyed, but one is destroyed faster than the other. And so you see, as long as you irradiate, both enantiomers becomes more and more small, but the He enantiomer is increasing. And at the end, one will be completely destroyed. There will be a very small amount of matter, the matter will become enantiomerically pure from the theoretical point of view, but the amount of matter will be very small. That is the first example of chiral reference, general chiral reference. But there is another one. This is the fact that another source of chirality lies in the earth of the matter. This is the parity non-conservation principle. What is parity? Parity is simple. You take a physical phenomenon with the coordinate x, y, and z, and you transform into minus x, minus y, and minus z. For many physical phenomena, this transformation is make nothing. So many physical phenomenon obeys to the parity. They cannot be changed by changing the parity. But there is in the nucleus an interaction called the weak interaction, which is responsible to the beta radioactivity, where the parity is non-conserved. It was found by Li and Yang in 1956, and by one it was demonstrated experimentally by Mrs. Wu in 1957. I explain the Wu experiment. The Wu experiment necessitates cobalt-60, and the cobalt-60 is a radioactive element which decay in nickel-60, emitting electron and one antineutrino. This antineutrino is a chiral particle. Okay, so she takes cobalt-60, put in a magnetic field at low temperature, and look at the emission of electron. And she discovered that most of this electron goes to are emitted towards the South Pole. So in the reverse direction of the magnetic field. If you look to the spin motion, for instance, you make a parity transformation of a particle with a spin, and you return and you obtain exactly the same. So this particle is identical from the parity point of view. In the Wu experiment, you make a parity, you have the Wu experiment here with the direction of the magnetic field, the direction of the emission of electron, and if you make a parity transformation, you reverse the electron direction of emission. So if the parity was conserved, we will find the same amount of electrons to the north and to the south. The fact that they go to the south means that the parity is non-conserved. That is the result of the Wu experiment. She was called the first lady of physics. The consequence of the parity violating of the parity non-conservation is a PVED. The PVED is a parity violation energy difference, and it means that due to the spin-orbit coupling, two enantiomers are not strictly identical. They will be identical if not considering matter, but antimatter. But the difference is extremely small, 10 to the minus to the 11 or 10 to minus to 20 joule per mole. But Martin Quark designed the principle of the direct spectroscopy measurement of the parity violating energy difference. I must say that it is so small that it cannot, it has not been experimentally realized until now. You see to see the difference between the parity violating energy difference between the two enantiomers S and R and their level of ionization is like to see a fly on the moon. That is about the order of magnitude. Is very huge. And so, what are the routes to natural chirality? Is it the tiny PVED with a fly to the moon, or the elusive circularly polarized light? I must say that we ignore, in fact, the circularly polarized light give a good result. It is obvious, but we don't neglect, in our opinion, we don't neglect this because it is a universal force, which is everywhere in the universe. But what we need is enantiomeric. No, what we need is a chiral amplification, enantiomeric excess amplification. In chemistry, enantiomeric excess amplification is more or less easy to do. It has been made by Kagan, by Geiger, by Bellman, Laponas. And if we consider an aldehyde, this aldehyde is prochiral. It gives a chiral carbinol using chiral auxiliary. This chiral auxiliary has an enantiomeric excess, but the chiral auxiliary is not the real catalyst. The real catalyst is either monomer or a dimer. And when there is, because there is matter redistribution between the monomer and the dimer, there is an increase of the enantiomeric excess. And looking at this diagram, if the heterochiral dimer is not so reactive, the result will be an amplification of the enantiomeric excess. And this is the principle of the amplification of the enantiomeric excess in organic chemistry. And this is also the basis of the so-called SOI reaction. The SOI reaction works on an aldehyde, but this aldehyde contains two nitrogen atoms. They will be useful because the product of the SOI reaction is an amino alcohol. It's like the chiral auxiliary, and the product of the soy reaction plays a role of the chiral auxiliary. There is what they call the asymmetric autocatalysis. And in the soy reaction, a low enantiomeric excess gives a high enantiomeric excess. That is thanks to the use of isopropyl zinc, which is a very reactive organometallic compound. So all these reactions must work in non-equilibrium conditions. The principle of the soy reaction is, you look here, the aldehyde, the soy aldehyde, and soy is using a very small amount of this aldehyde with a very small amount of the chiral carbinol, the product of the soy reaction, but with a very, very small enantiomeric excess, 0.0005% of enantiomeric excess. And he made a run, the first run of the reaction. Then he had more catalyst, more diethyl zinc, and again, after the first round, the enantiomeric excess has already reached 57%. And after the second, 99, after the third, 99.5. But what is very interesting is that both the enantiomeric excess and the amount of matter is increasing. So both the quantity and the quality of the matter are increasing in the soy reaction. That is very interesting. And here the explanation is the presence of a complicated scaffold made by the polymerization or the dimerization, the tetramerization of the derivative of this chiral carbinol. This is the secret of the soy reaction, thanks to the zinc coordination on the nitrogen compound. And so the beautiful property of the soy reaction is the possibility of absolute asymmetric synthesis. For instance, soy repeated 36 times the same experiment, but without initial catalyst, and never he found a racemic output. So what is expected in a chemical normal laboratory reaction is without a chiral auxiliary, we obtain a racemic output, but not in the soy reaction. All the products are either plus or minus, but all are optically active. And we, thanks to looking at the literature and taking into account of all is known on the soy reaction, particularly the presence of some crystal X-ray determination of the structure of crystal tetrameric compound, we designed the noble Terran mechanism, which is a mechanism of the soy reaction, which reproduce the main feature of the soy reaction, including the absolute asymmetric synthesis, the huge amplification of the enantiomeric excess. There is a second example of this huge EE amplification. This is the so-called Widma deracemization. This is Cristobal Widma from Madrid. And to understand the Widma deracemization, we must refer to the Gibbs-Thompson law, which stipulates that the small crystals are more soluble than the big crystal. This is what is called Ostwald ripening. Look at this picture. You see several crystals, smaller and bigger, and the smaller crystal dissolve slowly, the bigger increase, they dissolve again and disappear, and it remains the big crystal. And that is what's called the Oswald ripening. This point is important in the SOI deracemization. SOI deracemization occurs on conglomerate. Conglomerate, there is three kinds of crystal: the racemate crystal, the pseudo-racemate, where the R and S are mixed, and the conglomerate, where the crystal made of R and crystal made of S are separated. For the Widmer deracemization, the conglomerate is, you need to use a conglomerate crystal. And so the Widmer deracemization, so conglomerate crystal plus chirality, or racemization in solution. That is what it is needed in the Widmer deracemization. The two crystals must communicate in between. They go to the solution and they return to the crystal. They exchange the matter continuously between the solid phase and the solution phase, either versus a chiral compound or versus two molecules which racemize. We need to racemize the two molecules to let the two crystals to communicate in between. And what is the mechanism, a real mechanism of the Widmer deracemization? There are several processes: racemization in solution, dissolution, the growth of the crystal, the agglomeration of small crystal into big crystal. But what is important is attrition. Attrition is made by stirring very, very strongly using a glass bed into the mixture or mixing machine, because the secret of the Widmer deracemization is attrition. Because in this situation, the system is driven far from equilibrium, and the big crystals are broken into small crystals. They can dissolve and return to the other. This increases the speed of exchange between the two crystals. Now I do no. Let me. Okay. To finish, I would like to stress what is the common point between the SOI reaction and the Widmer deracemization. Both are spontaneous deracemization. I invite you to take a look at our chemical review, where there is a description of all the situations where an enantiomeric excess appears spontaneously in some enantioselective nonlinear system, when these systems are driven far from equilibrium. In conclusion, I would like to illustrate. No. I would like to illustrate the importance of the chirality by taking some word about the D-amino acid case. Everybody says that the life is homochiral. Is not true. In fact, the question is, D-amino acid, are they anti-natural? And the response is no and yes. Because in the living body, there are intrinsic racemization. And so for instance, there is serine racemase, and there is formation of D-serine and D-aspartate. In the good microbiota, there is bacterial racemization and formation of D-alanine, glutamic acid, D-serine, and D-aspartic acid. But also in our diet, there is naturally present D-amino acid, but also a large amount of D-amino acid in food processed. And there is also in our body an enzyme which is called D-amino acid oxidase to destroy if there are too much D-amino acid. But the D-amino acid are interesting for our innate immunity, but they are harmful because they allow the good barrier function to be destroyed. They are important in the neurotransmission, in the neuroendocrine process, but also they appear in the cognitive disease are too much. The D-aspartic is involved in aging. It is also involved in cancer progression, in tumor growth, but also in the cancer treatment. So in the conclusion, D-amino acid becomes harmful if their small amount is dysregulated. And to finish now, I must say that chirality is a transdisciplinary concept involving several domains, from elementary particles to molecular chemistry, life, and astronomical science. And I thank you for your kind attention. And it's time now to respond to your question. Yeah, if there are some questions. And thank you very much.
Thank you very much to you, dear Jean-Claude. Your talk has been very didactic, and it helped us to visualize, to easily visualize all the frame of importance for this topic, for this chirality idea and concept. Thank you very much. And yes, we have questions from people in the audience. So from YouTube, Jesus Alvarado asks you, how relevant is the study of chirality in other atoms different from carbon, like nitrogen, phosphorus, and sulfur in biomolecules?
Yes. In fact, in organic chemistry, the organic chemists want to make a large amount of molecule, most beautiful molecules. And I know that some of my colleagues made chiral phosphorus. In Toulouse, there is a school of all time ago, a school of chiral phosphorus. But from the point of view of biochemistry, not only carbon, but also other atoms, perhaps phosphor or some metals, also the organometallic compound can be chiral due to the shape of the ligand. So, for example, these octahedral metals, they can be chiral, and so it's some in metallic enzyme. The metal the chiral environment, and so all the atoms which does not racemize too rapidly, they can be chiral if the number of substituent is sufficient. The minimum number of substituents to have a chiral atom is 3, to have a pyramid, if the pyramid has no inversion. That is my response.
Excellent. Thank you very much. We have another question also from YouTube. You mentioned that chiral asymmetry would be transferred from the natural world to the living beings. What could be the reason? Just because it appears previous to the origin of life?
In fact, we don't know exactly. It is clear that it's more easy to make chirality from non-chiral medium. In the laboratory, the Widma deracemization and spontaneous deracemization, we have a lot of examples in our review. It's more easily to make some chiral mixture than to synthesize the life. Life has not already been synthesized, but chirality has been synthesized from nothing without the intervention of the chiral referent. But in this case, the question is that we obtain a stochastic distribution of right and left. In some time, it is not stochastic, because in the laboratory there can be contamination by some living some bacteria or dust coming from the living world, which are already chiral. So it's difficult to have this stochastic distribution when you make a spontaneous deracemization in the laboratory.
Okay, thank you. Thank you so much, Jean-Claude. We have another question from Hector Vasquez. It says, according to Soai reaction, the presence of racemic mixtures could be just a tiny moment in the history of the chemical interactions with the carbon atom?
No, in the Soai reaction, there is probably a spontaneous reaction, which is non-catalytic. At the very beginning of the Soai reaction, there is a very slow reaction, but non-catalytic, which gives rise to this carbinol, but in racemic mixture, 50-50, but very slow. But then this carbinol accumulate, they polymerize to give this tetramer. So there is a left and right tetramer. But this situation, due to the fact that it is autocatalytic, and also that the fact that the heterotetramer is non-reactive, the situation is unstable from the chiral point of view, and it needs to bifurcate on one side or another side. And if there is no chiral catalyst, as we have shown in this experiment, I can show you. Here, you see here that there is about the same amount of chiral compound, the same amount of R and the same amount of S. About 18 on this side, 18 on this side, or something close.
Okay, thank you. Again, Jesus Alvarado, it says, how to separate organometallic stereoisomers if many more than 2 species coexist? And also, is there a universal way to highlight an isomeric form, as in autocatalysis with zinc?
At the end of the Soai reaction, there is hydrolysis, so all the organometallic is destroyed, and then by chiral chromatography, the two carbinol are separated and the enantiomeric excess is measured. That's all. At the end, the organometallic is destroyed. Hydrolyzed because this compound is very, very active with water, and it's easily hydrolyzed. They use a mixture of water and ammonium chloride to give some acidity to the water to destroy this organometallic diisopropyl zinc.
Okay, thank you. Thomas asks, the SOI reaction and Viedma deracemization are laboratory experiments. Is there any scenario for a plausible prebiotic process?
For SOI reaction is not possible because the SOI reaction is very, very sensitive to water. For the Viedma deracemization, there is a lot of experiment made by with amino acid, sublimation of amino acid, hot, wet and dry cycle. That is, I think that the Viedma deracemization is a prebiotic candidate. More than the SOI. The SOI reaction is just for laboratory. It's an organometallic reaction for organometallic laboratory. But the Viedma deracemization is probably easy to perform, is more spontaneous. What we need to find is just the right compound and the right situation. I think that the Viedma deracemization or something similar can be a prebiotic candidate. I think that it can occur in a natural situation without the intervention of the mankind intelligence.
Okay, thank you, Jean-Claude. And just a tiny question from myself. I have curiosity about the chiral pool. This chiral pool is restricted to the 6 compounds you mentioned, or is it more abundant? Is there more compounds?
Yes, of course, it's more abundant. But on a slide, I cannot put all the chiral pool. Yeah, there are many, but you know, to obtain an enantiomerically pure compound from natural source is not so easy. So many chiral auxiliary, they are made from the chiral pool, and they are derived from the chiral pool to have a good catalytic effect and so on. But now, very recently, it has been published a paper by people from the Cambridge data, structural data from X-ray structure, that a lot of compound appear as organic compound. They appear as conglomerate. And as they appear as conglomerate, it is like the tweezer of Pasteur. They can be separated easily, and they say that it can be a new chiral pool. And it is also a spontaneous resolution situation for conglomerate, which appears sometimes in the laboratory. But they say that we believe that there are very few. In fact, there are many. They give a list of more than 1,000. This is a paper. The title of this paper is by Walsh, and this is a chemical review, very recent chemical review, about 6 months.
Okay, so it's a very big
The
business.
new chiral pool.
Excellent, excellent. Thank you very much again, Jean-Claude, for your participation. I hope you can be with us for the rest of the journey.
Yeah. I will remain as long as I can.
Excellent. And it is time to finish with this first part, with this first session of our symposium, and we will back at 11:30 in 15 minutes. Thank you very much. Please stay with us.